Hi, everyone. Now, in this chapter, we're going to be talking about derivatives. So, I think a really good approach to understanding what a derivative is to kind of start with something that we know. So, like, for example, let's say we have y. So, let me get a different marker here, like writing in black. So, let's say we have y as a function of x. So, what that means is like y of x is going to equal, some sort of function on the right hand side where all you have are just the variable x's. Okay. Now, here's what we know. We know a couple things. First, y is dependent upon x. All right. In other words, x is our independent variable, y is the dependent variable. Now, if x changes, then y is going to change as well. We know that. We don't know. It could change a little bit, it could change a lot. No idea. But what we do know is that if x changes, then y changes. So, to kind of abbreviate this, we could say delta x is going to be x2 minus x1. That is the change in x. Okay? Likewise, delta y is going to be f of x2 minus f of x1 if y of x is a function. Okay, we can come all the way back up here to the upper left-hand corner of your screen and just write f of x equals y of x, which equals some function of x, okay? Now, the key to this entire scenario, and I'm going to highlight the word, is this. Notice in both of these scenarios, x is changing and y is changing. And what that means is that if we were to find, I'm going to do this using a picture because I think a picture is awesome. All right, so here's my first point. It's going to be x1, so this will be f of x1. Then my second point is going to be like all the way over here. That's going to be x2, which makes this. Let me extend this a little bit. It's going to make that f of x2. We know that if we were to connect these dots, all right, we could find the slope of that line by taking f of x2 minus f of x1 all over x2 minus x1. Now, your entire life, you've been told this, all right? And what this actually represents, and we know it represents the word slope, but there's another way to say this, and hopefully, I am hoping that your previous math teachers have been really calling it this, because this is really what it is. I know if you've had me in the past, I drill this concept as much as I can. This is what we call the average rate of change of y with respect to x. All right. So, like I said, back in the day when you were taught about slope, okay, you could easily find it. We all know the slope y2 minus y1 over x2 minus x1, or in this case, since we're talking about functions specifically, it's f of x2 minus f of x1 all over x2 minus x1. Good. Now, you call that slope, but my perspective on this is that's fantastic. But what does that number mean? Like, what does that number represent? And that's why, and we're going to be doing like more word problems as the semester progresses. And I hate calling them word problems because there's so much more than that. They're like a little mini story that you can read about and try to figure something out mathematically. But that's really what this is talking about is now that you've calculated slope, that's great. What does that number represent? Okay. Also, The line that we created. Let me highlight the line that we created. All right. So here's the line that we created right here. That has a special name as well. And some of you may know this, some of you may not. That line that we created is called a secant line. So a secant line is a line that touches your curve twice. That's all it is. Now, sometimes we can write this slope of our slope of our secant line, okay? So I'm going to write slope of secant line, which is our average rate of change. All right? Sometimes we write this formula as such. The change in y over the change in x is going to be equal to f of x2 minus f of x1 all over x2 minus x1. Now, hopefully, in the past, you've had a teacher that also wrote this. We need to be very careful because x2 is not allowed to equal x1. And that is because if x2 equals x1, that denominator is going to equal 0. And you and I both know, cannot divide by 0, that's undefined, okay? However, we just studied an entire chapter on this idea of limits. All right? So a natural question would be, or should be at least, if we have this idea of a limit, what's going to happen to the slope of my secant lines, or the average rate of change? What is going to happen if I let the limit as delta x goes to 0 of delta y over delta x? Like, what happens? So I think it's always good to show you what's going on. All right, so here I have a nice little demo here going on. All right, and I'm going to explain what this is in a second. All right, so here's my demo right here. All right, I'm a big fan of Desmos. It's free. You can get it on your phone. So go ahead and do this. But on the left-hand side, okay, we have f of x equals x to the second power. So the blue line, or the blue curve, I'm sorry, is x to the second power. Very simple polynomial. Then I have a, which is going to be a point, and a is it's going to be I think it's this point right here, 1, 1. All right. H is going to be our step size. So let me go back into our notes and let me show you what I'm talking about here. Okay. So this is going to be a really fast drawing of this. All right. So here's our origin. That's 0, 0. Here is the point. We're going to call it 1, 1, 1. All right. H, all right, is going to be any step size in between 0 and 1 on the x-axis. All right. So all I'm going to do is I'm going to allow this point right here to kind of slide up and down on this curve respectively. All right. So let's go back to our curve. All right. M equals, now let me explain how I got this formula. And this formula should look extremely familiar to you. If you're sitting there thinking, oh, wow, look at that. That's the difference quotient. Let me show you how we derive the difference quotient. All right. Back to the notes we go. So another picture for us, because you know I love pictures. I am a visual learner at heart. It's just a shame that my artistic ability is absolutely garbage. Like, I cannot draw if my life depended on it. So I hope when I draw these parabolas and stuff like that, it's at least legible. All right. But here's what's happening here. Okay. This is going to be the point right here. We're going to call this A, comma, f of A. All right. Just an arbitrary point. It's going to be the very first one that I see. Now, here is going to be another point. However, notice that I went from a comma f of a over on the x-axis to the second point, and that's going to be in the positive direction, so I'm going to call that plus h. So this x value is let me write it like this, is a plus h. In other words, it's a plus a little bit more distance, which means this y value is going to be, let me just write the point now, a plus h comma f of a plus h. So that's that point right there. Now, if I wanted to find the slope of this secant line that I just drew, well, I know it's going to be a change in y over a change in x. Therefore, this is going to be f of a plus h minus f of a. That's just like f of x2 minus f of x1, all divided by a plus h minus a. And if you notice, I can do just a little simplification in my denominator, and I get f of a plus h minus f of a all over h. Hence, the difference quotient. That's a very famous ratio that we have here. Oops, that's supposed to be an O, not an A. So yeah, the difference quotient is unbelievably important for us, okay? Back to our graph now. So the other stuff is just y equals m times x minus a plus f of a. That's just the equation of a line, okay, in slope-intercept form. And finally, I have the 2 points that I have labeled here. So what I'm going to do here is this. I want you to focus on two things. First, I want you to focus on this point right here. I'm going to let it slide up and down, all right? And then I want you to focus on the slope. Now, we could easily calculate the slope by hand, but this is going to do it for us, and I think that's going to be good enough, okay? So here's what's happening here. If I allow this point to slide down closer and closer to the x-axis, notice that my average rate of change of the slope of this line is changing, which should make absolute sense. I mean, if I allow it to go all the way back up here, we'll go all the way up to the top. Notice that is a very steep line, and my slope is positive 1.206. That's a pretty positive slope. However, if I allow this to get really close to zero, notice how the red line is starting to kind of like flatten out a little bit. And that is also verified by the fact that my slope is 0.45. Here's the question, though. We know in that denominator, x2 and x1 cannot equal each other. So if I allow this second point to go all the way down to 0, 0, look what happens to my slope. It says undefined, which is exactly what we would expect. However, you and I both know from that entire chapter 1, we have this concept of a limit. And limits are always good as long as we meet a couple criteria. The left and the right-hand sides of the limit have to be the same number. Got to have a continuous curve. We have that here. So the question becomes, what's the slope of this line at exactly the point a comma f of a? Let me go back to my picture right here. What I'm really asking here is this. If I were to draw a line, and I'm going to do it right here in red so you can see exactly what I'm talking about. If I were to draw that line right there in red, all right, what is the slope of this line? Now, intuitively, hopefully, we know that this is the equation, y equals 0, and all horizontal lines have a slope equal to 0. All right? But here's the problem. If I go back to my graph, it says the slope is undefined. All right? So in order for us to fully understand, in order for us to fully calculate this, we need, and I'm going to try to, I'm just going to rewrite it again. So just let me write this out real quick. So in order for us to fully understand what's happening here, and to get that m equals 0 thing, okay, we need to take the limit and allow our step size, which is h. That's that delta x thing, okay? We need to allow this to go to 0. And if we do that, what we have just defined is called the derivative. And this is our definition. This is massive, of the derivative. It is read f prime of x equals, and then obviously the limit as h approaches 0 of f of a plus h minus f of a all over h. This is not to the first power. That is a prime. In fact, sometimes you will see it like that. Like it's like italicized. Okay? But that's what's happening here. All right? So I think what we should do is let's figure this out. All right? So here's what we know. Let me write an example here. Find the slope. All right? And this is going to be, I'm just going to say it. Find the slope of the red line at 0, 0 to the curve f of x equals x to the second power. All right? So let me go back to our picture real quick. All right, and here's what I did. I just went ahead and right down here at the very lower left-hand corner of your screen, I just typed in y equals 0 because that is the red line that we want to find a slope of. Now, like I said, intuitively, we should be able to look at this and say, well, it's going to equal 0. Now, let's demonstrate that. And then I'm going to tell you what that red line is actually called. It has a very special name. All right? So let's go back to our notes real quick. Now, in order for us to do this, all right, we're going to need this definition of the derivative thing up above. Okay? All right, so the first thing we're going to do, let's find f of a plus h. So, f of a plus h is going to equal, put your parentheses first, make your substitution. Now we know the quantity a plus h to the second power, that means a plus h times a plus h. So, after simplification and distributing, f of a plus h is going to equal a to the second plus 2ah plus h to the second. That's the first thing we want to do. Second is pretty straightforward. Find f of a. Well, f of a is just going to equal a to the second. And now, if we take the limit as h goes to 0 of a to the second plus 2ah plus h squared minus a to the second all over h and simplify this, you're going to notice something. Okay? So, after we simplify the a squareds, reduce, this gives me the limit as h approaches 0 of, and I'm going to put it in descending order, h to the second plus 2ah all over h. I can go ahead and factor out an h, which is fantastic. That's going to give me h plus 2a all over h. The h's reduce. I get the limit as h goes to 0 of h plus 2a. And finally, with direct substitution, I get 2 times a. Now, we already know what a is. Because remember, we have the point 0, 0, which is a, f of a. So, if we let a equal 0, notice we get f prime of x equals 2 times 0, which is 0. Okay? So far, so good. So we found our derivative. Now, The second thing that you're going to want to do, and like I said, I'm just throwing this at you. I'm going to give you a much more formalized way of doing this. I'm just zooming up real quick because they wanted us to, oh, I just did it. Perfect. They wanted us to find the slope of the red line at 0, 0. Notice our derivative, which is our slope, is 0. Okay? But now the question becomes, let's find the equation of the red line. Okay, now, let me go back to the curve real quick. We already know what the answer is. It's y equals 0. I typed it in. Let me demonstrate that to you. So, anytime you want to find the equation of any line, you're always going to have to use this. y2 minus y1 equals m times x2 minus x1. I mean, that's what you were taught a long time ago. But now you are in calculus class. You are no longer going to worry about this letter m. You are going to replace that with the derivative, because the derivative is the slope of that line. Let me scroll all the way back up real quick. Remember, here it is right here. If we allow this point to get closer and closer and closer, you are calculating different slopes of secant lines. Okay? All right, and now all that math is right here. It's all like it's right in the middle of your screen. That's what this is. Okay? Now, if we go back to our question, let's go ahead and let's use our information. We know the point is 0, 0, and we just calculated that our derivative equaled 0. So you get y minus 0 equals 0 times x minus 0. And just simple math tells you the equation of that line is y equals 0. And here's what everything that we're doing here is all about. All right? When you allow, let's go back to our curve. All right? Let me see. Let me change this real quick. Let's go from negative, or nope, I want to go from 0, sorry. 0 to 1, step size, 0.1 should be fine. All right, I'm gonna hit play now. So when we allow this distance, this h thing right here, when we allow to get this bigger, notice our slopes are increasing, okay? And we're getting this secant line thing, okay? But here's the beautiful part about what we're doing and how it pertains back to chapter 1. If we take this value and we allow this point, as you can see, this is animated. So as you can see, it's getting closer and closer and closer to the point in question. And in other words, we wanted a equals 0. Notice that that all these secant lines and their slopes are getting smaller and smaller and smaller. Okay? Now, if you think about this, let me pause this. Let me come back here. I want you to think about this in terms of look at the letter M, and I want you to think about what number is it approaching? Okay? Not what number is it? What number is this letter M approaching? Just like a limit. As you can see, this M is getting smaller and smaller and smaller. And if you're thinking about this and you guess, well, it looks like it's approaching the number 0, you would be correct. And what happens is this. We know that when the denominator equals the same exact values, we know we get a 0 in our denominator, which we cannot have. However, if we allow the limit, let me go back. If we allow this limit right here, if we allow that step size h to get infinitely smaller, not 0, but approaching 0, what we are finding, okay, what we are finding here is what we call, and that's what this red line is going to be. This red line is called a tangent line. And a tangent line only touches your graph once. Okay? So, all of your secant lines, and I'm just going to hit play here, all of these secant lines will eventually turn into a tangent line as the limit of h goes to 0. And that is the whole thing behind a derivative. Okay? Now, then this is a lot of theory, and the next section is going to be a lot of theory as well. We're going to learn some shortcuts to help us find this, because as you'll see, finding derivatives can get very tedious, very cumbersome very quickly. So thankfully, there are like some shortcuts. I don't want to call them shortcuts. I think it's a bad math word. I hate the word shortcuts. There are rules that we're going to learn, which is fantastic. But like I said, as you can see here, what's happening is this tangent line, or this secant line, is getting infinitely closer to the point that we're interested in, a equals 0. It's just, we know we cannot allow that denominator to equal the same value. So if we slap on a limit at the front of it, we completely get rid of that scenario. All right. So let me go ahead and let me show you some other examples of finding equations of tangent lines, because that's really what we're doing here. All right. So this entire first video is all about this central concept right here, which is finding equations of tangent lines. Now, recall a tangent line is a line that touches, it doesn't go through, it touches the function once. Okay, and we know, all right, that in order for this to happen, the limit has to exist. Okay, like we know this has to happen, and the reason for that is because in order to find the equation of a tangent line, here's what we need. We need a point. All right. And this is assuming that we gave you a function, because we're always going to give you a function. All right. But the first thing you're going to need is a point. All right. The second thing you're going to need is your derivative evaluated at x equals a. All right. So in other words, whatever that point is. So the point is going to be a comma f of a. And then you're going to take whatever this x value is, and you're just going to substitute it into the function itself. Okay. And then the third thing that you're going to need, all right, is going to be the point slope formula. And that is y minus y2. Oh, sorry. I'm thinking slope. Y minus y1 equals our derivative evaluated at a times x minus x1. All right. Now, if you want to get very technical with this, which is fine by me, this is going to be f of a. That's going to be a. Okay. But it's actually very simple and very straightforward. Okay. So let's do an example here. Okay. So here's our example. Let's find the equation of the tangent line to f of x equals x to the second minus 8x plus 9. Okay? So remember how to do this directly above. We need a point. We need the derivative evaluated at some value of x, and we need the point slope formula. And what I want is this. I want it evaluated at, let's say, x equals 1. Okay? So hopefully you have those steps written down. Number 1, let's go ahead, let's find our point. So all we have to do here is just evaluate f of 1 Wherever I see an x, I'm going to put parentheses first. Then I'm going to go ahead and make my substitutions. Substitute a 1 and a 1. That gives me f of 1 equals 1 minus 8 plus 9. And when you simplify that, 1 minus 8 plus 9 is 2. So our point is 1 comma 2. All right. Second, we need our derivative at x equals 1. So the only way that we know how to find a derivative right now is using the definition of a derivative. So f prime of x is going to equal the limit as h approaches 0 of f of a minus a plus h minus f of a all over h. So let's go ahead, actually. Yeah, let's do it step by step. And I'm going to do it in red. All right, so first, let's find f of a plus h. So f of a plus h is going to equal, remember, wherever you see parentheses for the variable x, then make your substitution. I'm going to substitute in a plus h and a plus h. Go ahead and simplify. A squared plus 2ah plus h squared minus 8a minus 8h plus 9. And as I scan this from left to right, there's really nothing that I can combine in terms of like terms. So I just go ahead and I leave it like this. Second, find f of a. Well, that's pretty straightforward. That's just going to be a squared minus 8a plus 9. And then finally, let me put boxes around these two. There we go. Finally, our derivative is going to equal the limit as h approaches 0 of a squared plus 2ah plus h squared minus 8a minus 8h plus 9. So there's f of a plus h minus 8 to the second minus 8a plus 9. And there is my f of a all over h. Now, before I go any further, I need to stress this, and I like really need to stress this, okay? In the top left-hand side of your screen, remember, oops, let me get a different marker out. Oh, sorry, that was my cell phone. I don't know if you heard that noise. Top left-hand side of your screen, always put the f of a in like parentheses or brackets, because if you have a function, you're going to be subtracting that entire function away. Also, if you're doing this correctly and you have polynomials, which is what we have here, this f of a will always cancel itself out. Let me show you. F prime of x equals the limit as h goes to 0. And I'm just going to go ahead and just rewrite it. I'm going to distribute first. A to the second plus 2ah plus h to the second minus 8a minus 8h plus 9 minus a squared. Here's the distribution part. Minus a squared plus 8a minus 9 all over h. And as you can see here, there's positive a squared and there's minus a squared. They will cancel themselves out. Here's negative 8a. Here's positive 8a. They cancel themselves out. And finally, positive 9 minus 9. They cancel themselves out as well. So that leaves us our derivative, which is going to equal the limit as h approaches 0 of, and I'm going to put everything in order, h to the second plus 2ah minus 8h all over h. And the beautiful part about this, look at the denominator. We know it's an h, and we know we cannot use direct substitution. However, In the numerator, every single term has an h, which means we are going to factor out an h. That's going to give us this. H times a quantity. H plus 2a minus 8 all over h. The h's reduce. You get the limit as h approaches 0 of 2a minus 8. Oh, sorry, I'm moving too fast. H plus 2a minus 8. And now when you use direct substitution, our derivative, f prime of x, is going to equal 2a minus 8. Now we need to evaluate this. We know our point is, or our x value of our point is 1. So I'm just going to erase this and just say, well, f of 1, make my substitution. F prime of 1 equals 2 times 1 minus 8, or f prime of 1 equals -6. All right? And here's what's beautiful about this. You ready? You got your point. Our point is 1 comma 2. We got our derivative evaluated at that x value, -6. We can then say y minus y1 equals our derivative evaluated at 1 times x minus x1 is going to be y minus 2 equals -6 times x minus 1. And just a little bit of algebra, y minus 2 equals -6x plus 6. Then we're going to add 2 to both sides to give us y equals -6x plus 8. And this is our equation of the tangent line at the point 1 comma 2. So what I'd like to do here is just go ahead and show you what this looks like to make sure we are correct. So let's go ahead. Let's go back over to Desmos. Got a nice blank screen here. I'm going to type in x to the second minus 8x. I don't even remember it. Was it plus 9 or minus 9? It's plus 9. Excellent. You're probably yelling in your room right now like, it's plus 9. I'd probably be doing the same thing, so don't worry. So anyways, we got x to the second minus 8x plus 9. Our point was 1 comma 2, which is clearly on the function itself. And the equation that we just found is the equation of the tangent line, which means if we are correct, then when I type in y equals -6x plus 8, we should touch this function at the point 1 comma 2. So let's go ahead and let's verify it. Y equals -6x plus, and look at that. That's a beautiful thing. I'll zoom out here just a little bit just so you can see it. Now I'm going to zoom in as much as I can. And as you, hopefully it's making sense that the further you zoom in on a curve, the straighter the line is going to get. So as you can see here, I mean, I'm really zooming in here. And I mean, eventually you'd get some separation. Let's see how close I can get. My gosh, we're zoomed in so much here. Yeah, it's so close. All right, I'm done zooming in. But you get the idea. You get the idea, which is a tangent line touches your curve only once. And then also I went ahead and this is our secant calculator right here. And if I go ahead and hit play, you could see that our slope is changing. All right. So right now it's like getting less negative, -5. Then it might also get down to like -4. All right. I'm just going to go all the way down there. Let me see if can I speed you up a little bit? Yeah, here we go. And as you can see, the closer that this secant line, the closer the secant line gets to our 0.1 comma 2, look at the slope. It is approaching -6. Now, if I'm good, I can stop it at exactly negative or at 1 comma 2, and I'm almost good. And notice it's -6.01. And as soon as you cross over, it's still really close to -6. But remember, we're talking about limits here. So in this example, these are secant lines, and we're allowing them to approach x equals 1. In this example, we actually figured out, okay, if we're standing at exactly x equals 1, what is the slope of the tangent line? And that leads us into our very last definition. All right. So your book does a really good job at showing this. All I want to do is show you where this is at in our book. All right. So right here in this picture, all right, when you see this Q, 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 what they're talking about are all the different secant lines. All right. And as you allow this point right here to get closer and closer to point P, you will approach this tangent line. Okay. So the tangent line to the curve y equals f of x at the point A comma f of A is a line through P with the slope m equals the limit as x approaches A of f of x minus f of A all over x minus A. Now, that is a tangent line. What we just found here is this. Remember, secant line. So let me go back to our book here, rates of change. That's what I wanted to go to. Perfect. So a secant line is the average rate of change with respect to x. All right. Sorry. With respect to x, average rate of change of y with respect to x. That is what a secant line does. However, once you find the tangent line and you find that slope, what you have just found is right here. It is called the instantaneous rate of change. In other words, all right, let's go back to our notes. In other words, when we calculated this -6 right here, what that number actually represents, all right, f prime of 1 equals -6. The -6 is the instantaneous rate of change at the point 1 comma 2. I need you to really take a step back and think for a second. Whenever you were taught how to find the slope, you always needed 2 points. You always needed 2 points. y2 minus y1 over x2 minus x1. How many points did we use here? Let me scroll up. How many points? Only one. We only had 1 point. You never ever did this prior to calculus class. You always had 2 points. So we no longer need 2 points to find the slope of a line. If we use 1 point and we use this concept of a limit, we combine those two together. We marry those two together. What we found is the derivative. And the derivative is the instantaneous rate of change. All right? That is unbelievable. All right? The instantaneous rate of change, you need to be thinking derivative, because that's what it is. It's the instantaneous rate of change at the point 1 comma 2. All right. So let's say we were making t-shirts, okay, and we know that if we make more than 100 t-shirts, all right, in 1 year, or I'm sorry, in one billing cycle, what this -6 represents is for each additional t-shirt, we're going to be losing $6 of revenue. That means the costs are starting to eat into the revenue, and then your profit goes down. All right. So let me write that down here. So in fact, I'm going to write it as this. Man, you have no idea how excited I am. If we were in class, like in a room, and I was physically in front of you, I would be like, not running back and forth, but I would definitely be like walking on my tippy toes, and my arms would be all over the place, because this to me is so unbelievably exciting. All right. So let me write this here. f prime of 1 equals -6/1, all right? Because remember, you can turn any integer into a fraction or into a ratio by putting it over 1. And here's what this is. We know this is the instantaneous rate of change, and what this says is for each additional unit, all right? We'll say 1 unit. For each additional 1 unit, we expect a decrease of 6 units. Now, whatever those units are, I have no idea, all right? I mean, for all we know, this could be, miles per hour. For each additional hour, we are expecting a decrease in speed of 6. Whatever that happens to be, okay? The fact of the matter is, for each additional 1 unit, that's our denominator. That's the delta x, that's the change in x. The decrease is the negative symbol. And then the 6 units, well, that's our change in y, which is our dependent variable. And that is what the first half of our semester is going to be about. We're going to be finding derivatives. We're going to be interested in one question. What is the instantaneous rate of change? Because if you go outside and you look at the world around you, it is not static. It is unbelievably dynamic. Everything is changing at all times. And it's always changing with respect to one specific variable. And it's the only thing we can't control. And that is time. So a lot of these questions will be using the variable x. And a lot of the questions we're going to be using the variable t for time. So everything around you is changing. The question becomes, how do we measure that change? Well, if you are just interested in 2 points in time, a secant line is perfect. Go ahead and use your traditional y2 minus y1 over x2 minus x1 slope that you learned in algebra class. However, if you were interested in the instantaneous rate of change, if you were watching who I think is one of the most amazing athletes that has ever lived, still living now, Usain Bolt. I have a special place in my heart for Usain Bolt. Because when I was in grad school, I tested my 100-meter race against his, and I'll just say it right now, it was disgusting. Like, it was so bad. It was so bad. Like, and I thought in high school I was a good athlete. I ran the 40 and 4.65. All right, 4.7. I was pretty quick. I am nothing compared to this. To compare to Usain Bolt. I mean, he's just unbelievable. And if you were watching Usain Bolt run a race and you took a picture, all right, if you could figure out exactly how fast is he moving at that moment in time that you took that picture, just by knowing a couple things, okay, you could figure that out. And it's unbelievably cool when you do that, all right? So I am not going to bore you anymore. With my stupid stories. All right. If you're interested, all you got to do is email me. And I don't know, maybe I'll just make a little video and I'll tell you the story and I'll upload it. That way everybody can laugh because it's very funny. My graduate, uh, my graduate career was very interesting because I was not like all the other people that I went to grad school with. I was always into sports and everything like that. So when I wanted to talk about sports, there was like nobody there to talk about sports with. Like, it just happened to be the class that I went with, which I think there were like 14 of us that started. And after a year and a half, there were only 2 of us left. so it was pretty intense nonetheless. But anyways, I'll see you in the next video. Understand that the derivative is the slope of the tangent line, which is the instantaneous rate of change. And if you can just remember these steps right here. Let me zoom out real quick just so I can find them. All right. Right here. This is the name of the game. If you could just remember these steps, to find equation of a tangent line, you need a point, you need the derivative evaluated at x equals a, and you need the point slope formula. This is going to be a very simple chapter for you, okay? The big problem becomes when these problems get tedious, you're going to be asking yourself, is there a better way? And the answer to that question is absolutely there's a better way. I will see you in the next video.